All right. Hello, everyone. I'm glad to see we've got it's like four different individuals on the call on the meeting live, so that's always good to see. Welcome to Thursday afternoon of what is it, week 3 of the semester. So let me go ahead and share my screen and we can get going. All right, you should be seeing my screen at this point, the Canvas module section for the class. I believe you can hear me as well. I can see my mic bouncing up, down in Zoom. If you have any technical difficulties, feel free to shout out or drop a line in the chat. So with that being said, we can go ahead and kind of get started with the evening. First, to kind of recap where we're at in the semester. First week, we kind of introduced the class and introduced the idea of linear programming models, mathematical optimization, why it would be useful to implement such tools. We spent a lot of time in that first week only talking about model development and did not spend much time actually talking about the solution of models. And so that's where we dropped in last week, where we talked about this idea of, okay, I create a model, now I got to go solve it. Well, typically in this class, we don't actually do the solving per se, as far as we don't actually write the solvers themselves. Instead, we're going to use pre-packaged solvers, if you will. I've talked about the MS Excel solver that's built into the Microsoft Excel application. And then also there are other solvers out and about as well, kind of from the Python, Pyomo, GLPK side of things that we are specifically using GLPK, the GNU Linear Programming Kit is what GLPK actually stands for. There's something you just address as GLPK within the Python Pyomo interface. But there are other ones. CBC comes to mind as well. There's the Groby one I talked about, relatively various open source as well as commercial options there. And so typically what you'll do, unless you go work for one of those solver companies, is you'll spend all your time developing a model, and then you go and pass it on to a solver. The solver solves it, and you get back a solution, hopefully. And in the context of linear programming, you're going to be getting back a optimal solution. Well, in this week, we kind of take a little bit of a detour at that point and basically kind of go from the side effect of, okay, I've solved a model. That's great. I know the values of the objective function, the values of the decision variables there, which form the optimal solution. But there's other pieces of information we can get out of this type of study, and it has to do with an area called sensitivity analysis or post-optimality analysis. And so that's what we'll dive into this evening to kind of set the stage, if you will. So the Chapter 3 module should have just unlocked, and you can see the content here. I've got a couple of YouTube videos that I've created on specific topics. You see range of optimality as kind of a vocabulary term, shadow price is another, and then reduced cost will be kind of these three concepts that we introduced for the evening. I've already got my Docker instance up and running, so I've got a running container of Jupyter Lab. That kind of starts at the root directory here. If you're following along, we're in lecture, linear programming, and sensitivity analysis is where you'll find the content for this evening. So I'll go ahead and get this started and go ahead and run the notebook here. So with that running, one thing I did want to make a statement on early on in the lecture, kind of at the administrative level before I forget, is now we're starting to get in the routine of having homework assigned on Thursdays and due the following Thursday. I think I've mentioned this before, but I just want to make sure that everybody's kind of aware of the obligations that I've got going on as well. I encourage you guys to start the homework as early as possible, preferably if possible, start tonight or tomorrow. That way it gives you time to start questions back and forth. The reason I bring that up is because once it gets to about Wednesday night into Thursday, it's pretty hard for me to get a timely response back to you guys in terms of feedback prior to the submission deadline. Take, for instance, today, I think I've got 1, 2, 3, 4 different student emails that have all hit. I assume they're about homework. They all hit since noon this afternoon there. So I'll go ahead and reply to these after this evening or tomorrow. But just so you know, it's hard for me to give you feedback in time for submission exams if you wait till, especially Thursday, even the latter half of Wednesday. to get timely feedback to you there. So just be aware of that as you kind of plan out your weeks and when you can work on the homework sets. All right, so with that out of the way, let's go ahead and actually talk about the content for the evening. As mentioned before, we're going to enter an area called sensitivity analysis, also known as post-optimality analysis as well, depending on kind of what book you pick up there. And the whole idea, again, is to solve a model. And assuming we're using real decision variables for that model, we can typically get additional pieces of information from the solver without having to resolve the model over and over again. And you may be asking, okay, what other additional pieces of information would I even be interested in, right? I've got the optimal solution. I've got the resultant value of the objective function. I'm kind of good to go, so to speak, right? Yeah, even last week, we talked about slack and surplus variables, right? I could potentially get those out of a model. I'd be kind of interested in those as far as if I had a department or some sort of limiting capacity in some area, if I was able to determine if that was binding or not, or if I had some unused capacity still left over. Those would be interesting things. But then there's other questions that can be had. Let's take, for instance, the look at the objective function. Well, when you're forming an objective function, some of the things we've seen are the ideas that the coefficients of that objective function are things like per unit cost, potentially, or per unit profit contributions. But what if you acknowledge the fact that, well, one of those objective function coefficients may not be known with complete certainty? What if there is some ability for that to vary slightly one way or the other? If you're off by, let's say, a couple dollars on a profit contribution, will that change my optimal solution? And by optimal solution here, think of the values of the decision variables, because obviously we know if I change the objective function coefficient, that's going to change the resulting value of the objective function there. And so that's something that we'll look at in terms and the concept of range of optimality for a given objective function coefficient and decision variable. Another thing could be said there as far as, okay, if I look now instead of at the objective function, I pull down into the constraints. Well, if I look at the right-hand sides of a lot of our constraints, typically those are like lower bounds or upper bounds in some ways, thinking of like less than or equal to or greater than or equal to inequalities. And so if I think about those, let's take the instance of it's a less than or equal to inequality. We've seen a number of these for like production planning type of problems where it represents a certain amount of labor in a department or the certain amount of some raw material that we have in inventory. And so if it is such that that material becomes binding, how much would I be willing to pay for an additional unit of that material? How much is that worth with respect to the increase that I may want to see in the objective function value? This is something we'll be learning about as far as dual values is what they'll be called, and shadow prices this evening. And again, it's important to note that these type of bits of information are not coming from repeated solves of the solver, but from this analysis that we can tell the solver to do afterwards being after it completes the solve. And so hopefully that kind of gets your mind in the right frame of state for the discussion this evening. And so with that being said, we'll start off relatively easily this evening and just talk about this simple LP model. In this case, I'm just giving you the model itself. You're not having to go from a problem statement for it and to solve it here. And we've got the minimization of 8x plus 12y subject to these three constraints, with decision variables are represented by x and y, and we'll assume that they're the elements of the real number system. And so hopefully at this point in time, with the homework set last week, you feel relatively comfortable being able to solve these either with a graphical method or a analytical method. If you want, we can go ahead and at least talk through some of these things just as a refresher from last week. I'm just, for the simple sake of ease, I'll just use Desmos here. You just kind of talk through some of it. And so the first thing I'm thinking of is, well, I need to write out my constraints, correct? And so each one of these constraints is splitting the Cartesian plane in half. And so Desmos here does a reasonably good job of shading the half of the Cartesian plane that satisfies this constraint. And so I'll go on with the next one. And finally, the third one. All right, so I have my three constraints here, and that's all looking good. And the thing that to think about is now I need to find what? The intersection of all three of these shaded regions. And so in this case, the intersection is basically going to be formed partly by this line segment between 0, 9 and 2, 3. Next kicked off by this line segment between 2, 3 and 3, 2. And then segment 3, 2, 2, 9, 0. And then, of course, we're bounded by the first quadrant, if you will, or the positive sides of the X and Y axes there. So it's all this kind of region in here that we would say is the feasible region from last week. And then we'd have to go about picking different values of the objective function and trying to solve it. If I scroll down a little bit here in my Jupyter notebook, I'll have done the same thing as before with the Plotly graphing library as well as a little NumPy. Remember from last week, some things we have to do. If Desmos just doesn't give us the ordered pairs, we may have to actually solve for those as a 2x2 system of linear equations given the lines associated with the inequalities. So that's what we're passing through here. And then we're showing the feasible region here. Then we could pick different values of the objective function. And here we'd be looking at a minimization problem. So we're trying to pick the smallest value possible. And it looks like it ends up being 48. Remember, a big key point from last week was this idea if I am talking about linear programming and I'm talking about real decision variables, then I am guaranteed that the optimal solution will occur at one of these vertexes or extreme points on the feasible region itself there. That is a very, very important property associated with this process that we're running. And if I believe I mentioned last time that this is all kind of credited toward work that was done by a guy named George Dantzig and the underlying simplex algorithm that he came up with there. And so in this case, we've arrived at the optimal solution. We said, okay, the optimal solution occurs at 3, 2, x and y, and the objective function value is 48. Last week, this is kind of where we stopped in a lot of cases. But of course, the whole point of this course is to build on top of each other a little bit. And so we'll start to pick up here and start talking about some other interesting bits of information. And this first one's going to be the range of optimality that you can see in the bottom corner here. And so the range of optimality is basically this idea that the objective function coefficients, so in this case, these guys we're talking about, if I just look at one of them at a time, so let's say we hold 12 constant and look at 8, how much can 8 float up and down and still have this point 3, 2 remain the optimal solution? And that's what this range we're talking about is the range of optimality, the range that decision variable's coefficient can fluctuate and again still remain optimal solution is the same value, in this case 3, 2. One of the things that I need to express, and I think it's stated right here, and I'll probably express it multiple times throughout the evening, is that when we're talking about these type of changes, we're only going to be allowed one change per model. And so what I mean by that is if I'm looking at this and I'm looking at range of optimality type of study, well, there's two different coefficients here, 8 and 12. If I'm doing this, I have to hold one of them constant, and I can allow the other one to continue, essentially to vary. And so I'm basically wanting to emphasize the fact that when I'm doing this range of optimality study, when I'm doing the dual value study, reduced cost will come later, it's the idea that only one part of the model, in this case, one coefficient of an objective function variable, one coefficient in the objective function for a decision variable can be the one that's changing. Everything else in the model has to remain constant. So that's one little bit of limitation of the model or the sensitivity analysis that we're going to be doing. And so with that being said, how would we go about determining the range of values that this can be take and still remain the optimal solution? And in this case, we are picking the x decision variable here. So we're specifically saying how much can that 8 float up and down while leaving everything else the same and still have the optimal solution at that 3,2 value. Well, one of the first things we'll need to do is think about these line segments that formed the feasible region. So it looks like it's formed, this vertex here is formed by this line segment here and this line segment here. If I go and kind of pick back over at Desmos, this is the blue line segment, and here is the red line segment here. So these two constraints, it looks like the first two constraints are the ones that are showing the model is different. And so that's dictated right here. You can see constraints 1 and constraint 3. Here all I've done is I've rearranged these algebraic inequalities. I consider them as equalities and solve for them in terms of this form of the line y equals mx plus b. The only reason I'm really doing that is I am trying to identify the fact that it's very easy now to observe the slope here, negative 1/3 and negative 1. So maybe we can do a little bit of sketch work here that might help to illustrate this. If I can get configured here. All right, so negative 1 and negative 1/3 are the relative slopes here. And I'm going to write it like this because that m, I mean, you may think of it when I write y equals mx plus b, is going to stand for the slope. And so if I look back over here, one of the things you may think about is, okay, what would cause the optimal solution to jump between these two vertices, for instance? Well, in thinking about that, and hopefully from last week you think about that a little bit, is just the idea that one of the things that influences this red line segment that forms the objective function is the slope of it, right? If the slope of this line is a little bit different, I could see this point now being the optimal solution, or this point, or potentially this point even. And so one of the things we would be able to kind of intuitively know is that as long as the slope of this line segment, the red line segment here, is between the slope of this line and the slope of this line, then we kind of rock, if you will, about that point, kind of pivot, if you will, and the optimal solution remains the same. And so now we just need to kind of flesh out that idea a little bit. And so to do that, let's come back over here. I'm saying, okay, the slope has to be between negative 1 and negative 1/3. Those are coming between the slopes of the binding constraints. But when I think of slope, what do I think of? Well, I think of it as a rise over a run. And to make that a little clearer with respect to what we got going here, I've got some objective function that may look something like this. Alpha x plus beta times y. I think this is an 8 right now, and this is a 12, if you will. But the reason I write it like this is because I can think, well, I can rearrange this a little bit. To something I believe like that, just to make sure I do my algebra right. Yeah. And now all of a sudden I have the slope, right? Negative alpha over x, or negative alpha over beta times x. Well, that's great because now I can substitute this relationship for here. And so I can say, okay, that's negative 1 is less than or equal to negative alpha over beta is equal to negative 1/3 there. In this case, I'm going to do a couple different things here. One of the things we said before, if I come back over here, is we were wanting to investigate the range of optimality for this value alpha. So we need to keep beta constant. If I remember right, beta I think was 12. Again, just sliding up here so I can see the model. Yeah, this is 12. So this is 12. This is 8 that we're going to see if it floats a little bit. So here I could say, okay, one thing I need to do is let beta equal 12. And then I also want to solve for alpha. So one of the things when you multiply these inequalities by a negative sign, what it flips the inequality. So I'm going to look at something that looks about like this. I will have alpha in here. And then I'm thinking about if beta is 12, I'll take the negative side with me. So it'll be negative 12 times, or negative 1/12 here. And I take the negative 12 and bring it over here. So that's 12. And the same thing here. If I have 12 over 3, that's 4. So that's going to be 4 right there. So hopefully that's all making sense. Basically, in one instance, I'm putting beta equal to 12, and then I'm just solving the inequality to isolate alpha there. And so what this is actually showing at this point is that our range of optimality for the decision variable x is the range of 12 to 4. So maybe I'll write that out just to be clear. Optimality for the decision variable x is going to be, we're going to be closed bounds here. So I believe it's this. It's usually lower than bigger, 12 to 4, inclusive. And so again, this is what we'd consider the range of optimality. So if I pull back over here graphically, hopefully I can illustrate this a little bit more to kind of make it more tangible for us. Here's the work we just did. And I want to get down to this image here. So what we have, as I start to click on these different x coefficients, is you'll see that this thing starts to rotate a little bit. Yep. And so what are we rotating about? Well, it originally was 8, so we were sitting right there. And if I increase it, notice it starts to rotate what would be clockwise from 10 to 12. And notice it stops when what? Well, it stops when the line segment associated with that new objective function is parallel to the constraint line segment there. And then I can also go the other way, right? If I go to 6, I go to 4, notice it's starting to rotate, if you will, in the counterclockwise direction. And now instead of becoming parallel to this line segment on the feasible region, it is now parallel to this line segment of the feasible region. But in all these cases, we are able to say that this same point, 3,2, is remaining the optimal solution for the problem there. Hence, we would say that this range of values for that variable, the x variable here, the range is from 4 to 12 inclusive, which is the range of optimality for that decision variable. And so hopefully that makes sense as far as why that would be of interest to you. I kind of related to it a little bit earlier in the discussion, the idea that maybe when you have your data gathering part of the exercise in real world example here, you have to make a few assumptions as far as the certainty of the decision variables and their objective function coefficients specifically. And you say, okay, well, I may have trouble characterizing the exact cost of maybe the labor cost of a given item that I'm selling, but I think I have a pretty good understanding of it. Maybe it's got a error margin of plus or minus a couple dollars. Okay, well, in the fact that I know that I have that error margin plus or minus $2 or $3 compared to some nominal value that I'm going to put in my model, is that going to be a big deal for me? Is it in such a way that that slope, we'll say, of the objective function is so close to one of the constraint lines that if it varies a couple dollars one or the other, I'm going to now jump to a new optimal solution or not? In this case, if I'm thinking about that the way I'd like to, I'd be saying things like, okay, if I get my optimal solution, I look at the sensitivity analysis, there was one coefficient on that objective function that I was a little worried about, and I knew it was like plus or minus $2 or $3. Well, if I look at the range of optimality and it easily covers the uncertainty range that I'm trying to have in my mind, then I don't worry about it too much, because I know that even at any extreme end of that continuum that I think that value will fall, it'll still land me at the optimal solution. I guess before we move on to, I think, a couple edge cases here potentially, I want to kind of pause and see if there's any questions, because this is the first kind of big concept of the evening, is the range of optimality. Okay, didn't hear any thoughts there, so I guess I will continue moving forward. So special cases, it was nice here, a nice teaching example here, because our range of optimality was kind of nicely bound, if you will, by two constraint lines. That definitely can be the case, but we can also have this case where I'm not bound by a constraint line, but maybe I'm bound by an axis. So like, what if my original optimal solution was at 0, 9? Well, here, if I rotate a line segment over here, that makes sense. I'll bound by that. But what happens if I over here? Because remember, we say our decision variables are usually greater than or equal to 0. So one of them would be bound by this right here, right? That vertical axis. Well, that will actually happen if I change my objective function to something like this. Same LP model, just flipping out the objective function, 50x plus 12y. In that case, I end up with, just like I described, an objective function like this if I follow the graphical method. The optimal solution is at 0, 9, and the objective function value is at 108. Okay, that's great. Now I play the same type of idea as far as the work that we did over here in the sketchbook. And I do my mathematics, same as last time. Oh, wait, I have a vertical line all of a sudden. Well, vertical line, when I think of my basic elementary algebra, if you will, slopes are rise over run. Well, in this case, the run is 0, right? It's all rise. I can't divide by 0. I trend off toward either positive or negative infinity in this case. In this case, these are negative slopes here, so I claim it as negative infinity. And what I end up with is a lower bound on my range of optimality. In this case, 36. And this is for, I believe, the x variable. Yeah, for the x coefficient. And then, oh, we're modifying only the x coefficient. Yeah, we're modifying the x still, keeping the y constant. The lower bound is 36, but then the upper bound here is off at infinity. This is definitely a thing that is possible. You can kind of see how the line segments rotate again. Here's it starting there at one edge, and then it'll start to continue on to sweep to closer and closer to the vertical as we increase that x coefficient there. It's not just one edge case you have to be worried about, that when you get a solver's sensitivity analysis report back, it is potential that one of those bounds is off toward infinity there. All right, so that is the range of optimality. We'll come back to the objective function here in just a little bit, but now we'll move down to the constraints section. And as you can see, that's hiding there at the very bottom of the slides. Specifically, we're going to be looking at the right-hand sides of the constraints. And typically, these were constant values that we were working with. And so I mentioned it before, but here's where you'll see it in the notes, is that this part of the LP model is typically talked about as far as the sensitivity analysis of William of those right-hand side values as either two different phrases. You'll see dual value and you'll see shadow prices. So if you see either of those values, either in the textbook, and then if you're comparing the textbook to MS Excel, for instance, I think it uses the term shadow price there. we're talking about the same actual concept there. And so what actually is it? Well, you can see that the definition there, that's again, for exams, I know we're in chapter 3, so you have chapter 4, chapter 5, we're about 3 weeks off from our first exam. There's a very high probability that there will be a question or two on the exam on dual value, range of feasibility, range of optimality. These are great things to grab for multiple choice, true, false type of problems when the exam goes. So just to keep that in your back pocket. And so the dual value, think of the amount of change that the objective function result will happen if I increase the right-hand side by a single amount, by a unit increase, as you can see there. So it's a very particular amount there. And so that's a very interesting thing to know as far as if I've got excess capital to apply to a model that after I've been solved, I say, okay, I can actually have a little bit more capital to spend. Where should I funnel that, right? Where do I get the best bang for my buck, so to speak, when I'm looking at my constraints and maybe limited resources that are at this point binding my solution? So not all values, or not all, excuse me, not all constraints will have a non-zero value. Think of some of the constraints we saw last week in the problem. Well, if I've got a constraint that's not binding, well, it doesn't really make any sense to throw any money at it, so to speak, right, to increase its capacity because it's not the limiting agent, if you will, in terms of the LP model itself. And also when we think of this, we're going to think of this as a amount that the objective function value will increase. Well, I can't just take that as a certain increasable rate and apply that forever. There are certain bounds on it. So just like we had bounds on these decision variable coefficients in the objective function, we call it the range of optimality. Here, the shadow prices or dual values have a certain bounds with which you can kind of extrapolate using this value, and it's called the range of feasibility. And so to look at this graphically, let's again take a very simple LP model, minimize 8x plus 12y, subject to those 3 constraints. X and y are real decision variables greater than or equal to 0. And if I look at it, we're going to be playing around with constraint number 2, the middle constraint there. And specifically, we want to take the right-hand side value from 10 to 14. I believe this is a very similar model compared to what we just solved, except for we just modified that second constraint. And so we can go through this same exact process. We can go and solve it graphically. We can solve it in MS Excel or with Python, PyMO, GLPK. I believe the graphical solution here is down. This is what I'm paging through here. So I'll go pretty quickly here and stop right here. So what am I looking at right here? Well, the combination of these 2 polygons, I'll say, is the feasible region that we just looked at before. So if I look at it, this is 3, 2, right? That was the optimal solution before I tried to mess with or alter the right-hand side of that constraint number 2. So what happened to that constraint number 2? Well, we increased it, right? We increased it from 10 to 14. Well, by increasing it from 10 to 14, remember this is a minimization problem, so it's going to push that boundary up this way. It pushes it up this way so that now the new feasible region looks something like this. All right, we can still solve this in the same way we solved previous graphical solutions. That's easy enough to do. And so we can go through, pick different values of the objective function, trying to make them smaller and smaller until we end up with this guy here. If I look at this for a little bit, that would make sense that that's the new optimal solution. Remember, the previous one was a 3-2 optimal solution. I think the value was 48. Now the new optimal solution is moved to 6-1. And notice the value of the objective function here is 60 from the legend of the chart. So if I think about this a little bit, I have now taken the objective function from 48 to 60. That is a difference of 12. The objective function increased. So the objective function is increased by 12. That constraint's right-hand side value went from 10 to 14, so that increased by 4. So the per unit increase that I would say for that constraint's right-hand side value is 12 over 4, or 3. So we would consider this 3 value to be considered the dual value for that constraint number 2. Okay, yes, we have to do a little bit of checking there. You may have jumped to a conclusion being like, Brock, okay, you said that's good, that all sounds good, but there was this range of feasibility. We didn't really check that explicitly here. I do agree. We didn't check that here. And so when we get into the computer solution here, very quickly, I'll show you how that gets shown to the user. And in this case, we can confirm that it is indeed within that range of feasibility. All right, so before we dive into the computer solution again, I'll take a quick pause here and I'll actually grab a drink and see if there's any questions on the initial discussion of the dual value, shadow price, and range of feasibility. All right, so not hearing any immediate questions, that's all good. But again, if you do have any questions at all, definitely this is the time to ask. That's what you're somewhat paying to be in the class, to be able to ask questions and hopefully understand the material as best as possible. One other note that I will make here, I'm not going to dwell on it very much just because we don't talk about it in a large extent in this class. But one of the things I do encourage you to do, if you're definitely interested in this subject area, is to grab other books that talk about this stuff. You can see a lot of different examples, a lot of different mathematical examples, but also just industry type examples. Those are always good to see. But you may see different terminology and different concepts that's not presented in our book. Our book is very much a introductory book to the course, not specific on linear programming, and definitely is kind of a survey style book in a lot of ways to the ideas of operations research. And so one of the things I do want to point out is why is it called dual value? Well, just so you know, every one of these linear programming models that we're talking about has I'll call it a brother type of model that is very similar to it, and the two of them are related, kind of like brothers are. That's why I use that term, and they call that the dual model. You'll also hear this idea or this principle of duality in linear programming. And so some of the ideas is that for this dual model, when you look at it, you can get information about the sensitivity analysis, the sensitivity analysis is giving us, such as the dual values, as opposed to when you're looking at this other parent model, if you will, or other brother model that we're really focusing on in this class. So this idea of dual is coming from that idea. All right, so with that being said, let's kind of revisit this. We've done things graphically. I've mentioned before in the class that we'll do a little bit of graphical stuff early on in the semester, but very quickly we'll move off to doing things with the aids of some sort of computer software package, not just to draw lines and fill areas on Cartesian planes, but to actually do the solving. And so at this point, I guess I'll go ahead and look at the MS Excel solver first. You've probably gathered just from our bits of interactions that in a lot of ways I prefer using the Python tooling just because I can see the benefits that it has with respect to scale of problems. One of the things that I do look at this week is I actually do favor the MS Excel solver here, largely because of the way it formats the results. And I'll show you that as we talk through this section 3.3. So what I'll do is I'll just first go ahead and solve this the way we have been doing it and show you how you can get the sensitivity analysis in Excel. All right, so it's a very simple model. So I'll just say I've got some decision variables, X and Y. I've got an objective function that I want to minimize some linear expression here. Like so. And it looks like we've got three constraints here, all greater than or equal to x plus 3y, 2 times x plus 2 times y. Hopefully at this point in the semester, this is becoming more and more natural to you. I definitely encourage you to experiment with the Python side of things as well. All right. So we've basically done all our worksheet work with respect to the model itself, and now we go to our solver. So as in data, the solver here, we need to set the objective function to here. We are trying to minimize. We want to allow the solver to manipulate those two cells. And then we'll add a series of greater than or equal to constraints. All right, so that's all good. We do want to make unconstrained variables non-negative, so that's good. And we'll hit the simplex LB solver. All right, 3, 2, and 48, right? That should all sound very familiar. That being the original solution we hit right here, 3, 2, and 48. So, okay, we've been able to validate our initial solution. Okay, now we need to go a little bit farther, right? This is not week 2, this is week 3. And so last week I said, okay, yeah, you can just hit okay. But this week I want to take a look at some of these reports. So I'll just go ahead and show all the reports for now. So the way Excel does this is that you can select the individual reports, you can hit OK, and it'll put them in different sheets or worksheets down below. So if I scroll this out here, I've got the original sheet 1, and then I've got a limits, a sensitivity, and an answer report. If I go to the limits report, I can see things like, well, I've got the optimal solution there, the value of the objective function, some other bits of information. The answer report, hey, this is kind of nice, considering the ideas that I've got the objective function, I still have the optimal solution. I do have the note from the solver. This is something that won't really matter too much right now, but will matter a little bit more when we get into problems where the decision variables can become integer or binary in nature. So one of the things that you'll have to worry about then is whether the solver solved and converged on the true optimal solution, or did it stop prematurely and just satisfied something we'll call the MIP gap when we get there? So that's interesting. And then this is kind of interesting down here. If you look, it's actually telling us what constraints are binding in this case. And so now that we have two decision variables, we'll have two binding constraints there. I believe that is also a nice mathematical thing that is very firm in the modeling process here, is that the number of decision variables and the number of binding constraints are going to be equal in count. Also here, notice they have slack. We talked about slack and surplus variables last week, so that's showing you that. Notice when we talked about binding constraints, the slack or surplus variables have a 0 value for slack or surplus, and so that's what we're seeing there. And this constraint number 3 has what would be what? It would be a surplus in this case, of 4. Yes, the header is slack. Excel doesn't make a difference or doesn't make a distinction on whether it should be labeled as slack or surplus for less than or equal to, or greater than or equal to constraints. So when I get asked questions in this class, I do request that you make that designation there. So remember that part, that if it's greater than or equal to things, then that is a surplus variable that we talk about. If it's less than or equal to, it's a slack there. And so I intentionally skipped over the last one, which will be the one that we will talk about the most this week, and that's the sensitivity report. Hopefully that kind of caught your attention very early on, since I talked about this as sensitivity analysis or post-optimality analysis is what we also talked about it as. All right, so let's look at these two tables. Obviously, I have a table at the top for the variables, a table at the bottom for the constraints. So every row here becomes a constraint, and every row here, or excuse me, every row here becomes a variable, every row here becomes a constraint. The variables are pretty easy. It's somehow getting the name here, but it's looking at the cell above it. It's also getting you the cell address they're in, so that's obviously a very easy way to do it. Here, I haven't done too much investigating, to be honest with you, as far as how Excel gets the name of the constraints, but they're all saying left-hand side, so it's looking at that header there. So the easiest way for me to figure out is, hey, constraint 1's in row 13, 2's in 14, and 3 is in 15. And so that's how I can marry those up to these rows there. All right, so let's first look at the variables table here. Obviously, I've got variable x. The final value is 3. and the variable y, the final value is 2. So this is telling me the optimal solution. The current objective coefficient is 8 and 12. That's just pulling right here and here from the model. So that's pretty easy. And then notice what I have here. Allowable increase and allowable decrease. Well, what does that mean? Well, from our talk a little bit earlier, this is how Excel is telling you that range of optimality. For instance, I think before we were looking at the coefficient that was in front of the X decision variable when we were talking about a range of optimality and doing our work associated with that. That's actually in the sketchbook here. And we said it ranged between 12 and 4. Well, it's presented slightly differently, but it's the same information here. Here's the allowable increase of 4. Well, that increase is applied to the current value of the objective function, coefficient. So 8 plus 4, there's my 12. That's the upper bound of the range of optimality. And then notice my allowable decrease is 4 here. So 8 minus 4, that is the lower bound of the objective coefficient for that decision variable x there. Same thing can be applied for y in the decision variable. All right, so with that being said, let's go ahead and come down here. Again, constraint 1, constraint 2, and constraint 3, how this gets mapped from the sheet 1 that actually holds the model. All right, so final values 9, 10, and 22. Well, those can be used to figure out a little bit of the surplus values in this case, right? Notice here, 9 here is right here as well, so that's binding. 10 here and 10 here, that's binding. I think before we said a surplus of 4 here. Well, we can see that right here, right? The final value is 22 and the lower bound is 18. So there's our 4. Well, here we go. Here's the shadow price, also known as the dual value. So we're getting those right there. Notice the 1 again that is non-binding has a value of 0, so that makes sense. In this case, 3 and 2, so it is more beneficial for us. Well, I guess I have to be careful here because I was about to say more beneficial for us to look at the number 3 there. But in this case, it is, but we have to be careful with what we mean by beneficial, right? We talked about the dual value or shadow price. If I come up here to the definition, to be the amount of a unit increase. Change in value of the optimal solution's objective function result per unit increase in the right-hand side value. Well, in this case, the 3 is a larger magnitude change, but typically, since it's a minimization problem, we'd want to be taking away from the right-hand side value instead of adding to it there. So that comes into play with the range of feasibility, which is described here. And so what I'm seeing there is, okay, for that second constraint, I would expect the result of the objective function to decrease by 3 if I can change this 10 here to a 9. But notice I can only make that extrapolation down by 1 count because I've got an allowable decrease of 1 here. I can go the other way and increase by up to 8. But since this is a minimization problem, you, of course, wouldn't want to be doing that. Also here, we talked about kind of edge cases where you can have it to where the range of feasibility or range of optimality is bounded in one way, shape, or form. Well, this is kind of what we're seeing here. Notice it has a very large decrease for the allowable decrease on the range of feasibility for third constraint there. Okay, so any questions for what I've covered so far in terms of how to interpret the sensitivity report with MS Excel?
Hi, professors. What about the dual values? It appears in the solver sensitivity report 1.
The zero values,
The
these zero values.
dual values 3. How is performed in the sensitivity report 1?
Okay, so again, I'm trying to understand what you're saying. That which zero on the screen? What cell are we talking about by chance?
I'm talking about constraint 2 and the dual value of constraint 2, E3, and
Oh,
how
this.
can
Okay, go on. You're asking where does this come from?
and and how it is mean in the Excel sheet sensitivity report one.
I guess I'm getting lost in sensitivity report one. Yes, that's the report we're looking at. This 3 value and the shadow price, that's your question. Is that correct?
Yeah.
Yeah. This is the dual value. Also, I could have labeled it as dual value right here. And so the idea here is if I was to change the right-hand side of this constraint, this 10, and if I was to increase that to 11, I would expect to see my resulting objective function value, the 60, go from 60 to now 60 plus 3 or 63. And I could continue that increase at a unit rate of 3 up to 8 times. Does that make sense?
Yeah, I understand now. It means that it could be increased 24,
Yes, that would
but
be the max, and that would be at your upper end of that range of feasibility.
yeah, okay, I
Which
understand.
in this case, since we're talking about a minimization problem, we'd want to be decreasing that value, but that's the same idea. I guess any other questions or concerns with what we're seeing or talking about? Okay, so we'll come back to reduce cost, but I want to table that just for a moment. One of the things I mentioned a little bit earlier is, okay, this is one of the few times that I favor MS Excel, and that's partly just because of the amount of work that's been done to the Python's solver. And so with that being said, I'll give you a glimpse if you go that route. And so inside of this week's folder, I think this would be a good one to look at. Same problem here. You've seen me write code looking similar to this to actually solve for the optimal solution. I can get to the same optimal solution value, 3, 2. Here is the optimal solution values. I think 48, if I remember right, with the objective function. But notice here there's not a whole lot of information with respect to the sensitivity analysis we've written. And so to actually do that, we're used to writing something like this, and then we just kind of said solver.solve the model, something like this. But now notice here I'm adding in 2 additional bits of information. And so you have to kind of understand where Pyomo sits in the stack here, if you will. So Pyomo is a algebraic modeling language. It sits on top of a solver. Pyomo doesn't actually solve the models, but allows you to write code that looks pretty nice and then be able to translate that into something the solver can understand. Well, a lot of these solvers have different options that you can pass down into them, which control certain settings. And so that's what this syntax here is doing. It's saying, okay, solver, I'm going to create options. Options is basically a Python dictionary, so think key value pairs. And this specific GLPK solver has certain options called output and ranges that allow you to export sensitivity type information out. And so what you pass these things are just files. These are just going to be text files here. I think I actually have them here as examples, here and here. So when the model gets solved, it basically solves the model like we're used to, but then it also spits out these 2 files or writes them to wherever location you're interested in. And so this is where the sensitivity report looks. Yes, it doesn't look near as pretty as the other one, but the information is still there. And so that's where if you look at this Jupyter notebook, I'll start picking through these things and say, okay, well, if I'm interested in the range of optimality, where do I go find it? Well, it's got a section down here that talks about the columns and it talks about the rows. Here you have to be a little bit more knowledgeable as far as how these LP problems are represented in the solver itself. A lot of them are represented in a matrix type form where the columns represent the decision variables and the rows represent the constraints and objective function in there. And so this 12 and 4 here is representing the range of optimality for the X decision variable, and this 24 and 8 represents for the Y. So that's where we're looking at 2 different outputs here telling us the same thing. A reduced cost we'll get to in a little bit, but Basically, Excel is telling me 0. If I look at this objective coefficient marginal value right here and here is going to be where that's at. Here, the objective function and marginal. The objective coefficient is the top value, just to be clear, and the marginal is what would be considered the reduced cost there. That's the bottom value. Here, instead of putting a 0, they actually put a dot. Shadow prices, dual values. Notice I'm looking here at the sensitivity analysis report. There's the slack, and then again, the marginal is what we're referring to here. So that marginal is what we call the shadow price or tool value. I've got constraints 1, 2, and 3 listed here. Notice 2, 3, and 0 from Excel. And there's my 2, my 3, and my 0 there. So for the most part, it's all here. Same with range of feasibility. Range of feasibility is also in here as well. And so you can get all this same information out, but I think everybody would probably agree that, at least for now, this on the right may be slightly more readable than the thing on the left-hand side here. It just kind of depends on where you come from. This could be probably dressed up a little bit. I imagine there's probably a way to somehow designate the row name so you could get that information in there as well and make it a little more readable. The other thing that I've thought about over a time as well, this is a fairly well-structured text output. Conceivably, you could write a little bit of a Python script to basically scrape this raw text output and get into a more general or more formalized, more, I don't know, better looking, more appealing table than what you're seeing off to the right here. Okay, so with that being said, 522, let's go ahead and talk a little bit about reduced cost, I believe. But first, let's make sure we cover all the notes. Yeah, we'll get right there. All right, so next is reduced cost. This value here, it was both 0 and the one above, but let's work on a problem here in a little bit where that reduced cost will not be 0. And you can see the definition here that you'll want to become familiar with for the exam. The reduced cost is the dual value for the non-negativity constraint for a given variable that we're talking about. So you can see why we kind of saved this for last, because we had to talk about dual values and shadow prices before that definition really made sense. And so notice it's the dual value for the non-negativity constraint. Again, we will basically state that on almost every decision variable we write the entire semester is that they will be non-negative. And so we'll talk about this dual value. So what does that mean? Okay, the dual value was the per unit increase in the value of the objective function for an increase in the right-hand side value of the constraint. So now we're kind of using that same idea. So we're thinking, okay, it's the per unit increase of the objective function, but now the value of the right-hand side is the non-negativity constraint. So it's moving that 0 to like a 1. If I move that x is greater than or equal to 0 to x is greater than or equal to 1, what is that going to do for the objective function? Well, in this case, if I look over here on the right, the problem we've already solved, well, the final values for the optimal solution are 3 and 2. Notice none of those are 0. So if I moved the x is greater than or equal to 0 to x is greater than or equal to 1, well, it's not going to change it because the optimal solution is not at 0, it's at 3. So 3 will obviously be greater than or equal to 1. So that's why they're both 0 in this case. But we can play around with it a little bit as far as the model itself that we're working with and come up with a model that is going to challenge that a little bit. And so I'll just show the model at this point. What if we change the golf bag problem that we talked about last week? We talked about par ranks golf bag. Last week, I believe they just had a standard and deluxe bag offering. They had certain operations they had to go through, and there's a certain total capacity in each operation and a certain total consumption amount as far as of labor for each golf bag style. Well, what if we add a third one to the mix? Now we have standard deluxe and we add in the lightweight golf bag. All right, so it's going to require differing amounts of time, we'll say, in each operation. And we'll have differing profit contributions, 10, 9, and 12.85 for the standard deluxe and the lightweight bags. All right, so that's all looking good. We can write a linear programming model just the same way we did last time. It very much will follow the same ideas as far as you'll maximize total profit contribution there and the top objective function. subject to a series of constraints. Each one of those constraints reflects the limited capacity that you have in each operation, where the left-hand side is how much of that operation's capacity you're consuming, and the right-hand side is the total available. So that all hopefully looks very familiar to you. This is one now that we've introduced a third decision variable. You wouldn't want to try to do it graphically, but you'd want to go strictly to a solver of Excel, GLPK, so on and so forth there. So let's just say we go through and we solve this model. If you solved it, you would see something about like this in the sensitivity report inside of Excel. The final value would say, okay, create 280 of the standard bags, 428 of the lightweight bags. And so this, since we have 0 of the deluxe bag, results in a non-zero value for the reduced cost, negative 1.15 in this case. So we're maximizing total profit. What does this mean? Well, this means that if you were forced to make a deluxe bag, you're going to suffer or decrease the overall profit by negative $1.15. Because what? Why? Because you're pulling resources away from an operation that could have been used for a standard and lightweight bag there. And so that's one way to think about it. The other way to think about it is, well, how much would I have to increase the profit contribution for these deluxe bags? Currently it sits at 9, you can see right here, in order for them to possibly show up in a objective, or in order for the deluxe bags to show up in an optimal solution. Well, you have to increase by the amount of this negative value. So add 1.15 to 9, 10.15, and I would expect to see the X sub D to show up in an optimal solution. Yes, and that's where we're at here. And again, I already showed you, I believe, in the Python and Pylomo GLPK, the area of that report that showed the reduced cost there. So again, that rounds out all of the big concepts that we're introducing for the evening. Again, you've got the range of optimality, you've got the dual values or the shadow prices, and then this last one is the reduced cost. All right, so before we move on, let's talk about some limitations here, and then we can take a bit of a break. Section 344 talks about these limitations of classical sensitivity analysis. This all sounds really great, and it definitely is powerful, but there are some things that have to happen in order for this type of analysis to be put in place. One, you're going to have real decision variables, which is something that just in the point of the semester we're at, all of our models deal with real decision variables. And the second one is simultaneous changes. Well, they're basically not allowed. You basically are only allowed to change one coefficient or one right-hand side of a constraint at a time, and everything else in the model has to remain constant. And so you do have to be careful about that. You can't be saying things like, well, I'll change, for instance, up here, I can't be running a what if scenario and say, okay, I'll change that 10 to 9 and this 12.85 to 15, and then what happens? No. You can only make one of those changes at a time, independent of the other. The other thing is, when I look down at the constraints, this is talking about here, notice we've talked about the objective function. We looked at the constraints. We only talked about the right-hand side. This classical sensitivity analysis does not provide us any way to do any analysis on kind of the left-hand side of those constraints. These would be things like, well, what if this standard golf bag only takes a half, or not 7/10, about 0.5 hours inside of the cutting and dyeing apartment? I'm sorry, at this point, we don't have any information from the sensitivity analysis, so you'd have to resolve the models. Again, at this point in the semester and the size of the models we're talking about, that's not a big deal, right? I mean, I've solved the model here this evening, and it took a matter of maybe fractions of a second. So you may not really grasp the full extent of the power of that. But what if you're working on a really big model where the time to solve is non-trivial? What if it takes 20 minutes to solve a model? Well, then it makes more sense to do this post-optimality analysis because you don't want to basically spend another 20 minutes waiting for the next solution. And finally, non-intuitive dual values, the last point to be made here. The dual values, you have to be careful with it because we're talking about a unit increase in the right-hand side value. We've seen it so far this semester that sometimes those right-hand sides are percentages. I think we had one where it was like, well, this amount, I think it was in a marketing type situation where the amount that you spend on the TV ads must be at least 30% of the overall amount of ads spent. Well, when I say a percentage like that on the right-hand side, it's very easy to fall into the trap that, okay, a dual value of that means 31%, right? 30% plus 1 is 31%. Not exactly, right? Because 30% and 31% are not necessarily an increment of 1 in terms of the actual value, right? It's 30% plus 1 unit is what we're talking about there, which can be very different than 31%, depending on the total population there. So just be careful about that when you're interpreting those type of constraints, because it's very easy to fall into that logical trap there. All right, so that brings us to the end of really the big discussion part of the evening, where we're talking about sensitivity analysis. I guess I'll turn it over to you guys to see if there's any questions or concerns over all this conceptual stuff that we're describing this evening. Okay, I don't hear anything at this point. At this point in the lecture, I think we just have the case problem left, so we're doing pretty good. I could probably stand to take a quick break too as well. So let's look at this guy. Let's do 8 minutes. I think that'll get us to 5:40 roughly. All right. So there's our climber clock. It's 5:32 now. We'll resume basically at 5:40. So great time to get a drink, stretch your legs, and we'll hit our case problem when we get back. Okay, so the timer's down. Mic is popping up and down, so I believe you can hear me. And we'll get into the last part of the lecture. But before we do that, I'll go ahead and save this off real quick before I forget. Very good. Close this down. Just do a little housekeeping here. All right, I think we're good at this point. Okay, so we're going to look at a case problem, basically a problem in the very back of the Chapter 3 homework set. Um, and we'll basically solve the model. We'll have to first create the model, then solve the model, and then we'll look at some of the sensitivity analysis type questions related to it. So if you want, you can turn to roughly page 136 in the course textbook. You'll see this product mix example from a fictional company called TJ Incorporated. They're looking to produce a different nut mix products. And so product-wise, you can see they have regular, deluxe, and holiday products. These products are made of mixes of certain types of nuts. The nuts in this case are the almond, Brazil, filbert, pecan, and walnuts. And so we can look, or looks like we've got a shipments coming in, various pounds of each one of the nuts you can see in the middle column here. The cost per shipment here is also located on the right-hand side. Noteworthy comment here is that we are contractually obligated to accept the shipments regardless of any product production. What I'm taking that as is I could sit on my hands right now, not fire up the factory, not do anything. But I am obligated to pay the $7,500, for instance, for almonds, $7,125 for the Brazil nuts, so on and so forth there, just because of my contractual agreements I've already made with the vendors themselves there. All right, and then also kind of the bill of material side of things, you can see here that the distribution across the different nuts of the regular product is listed in this row, deluxe, and the holiday here. All right, so profit contributions are also things we'd be interested in potentially. So $1.65, $2, and $2.25 for regular, deluxe, and holiday mixes respectively. They don't consider the cost of the nuts in these numbers here, so that's noteworthy. And we've got some existing customer orders here. It looks like 10,000 pounds are needed for the regular product. Deluxe is 3,000, and the holiday is $5,000 there. All right, so given this problem statement, we would now need to formulate a linear programming model. So let's see if I can kind of get these screens side by side here, and we can continue with the discussion. Go. Okay, so case problem one, product mix. As we go from a written statement of the problem, we need to formulate a mathematical model. So one of the first things we need to do is look for those controllable inputs or decision variables. So in this case, kind of take the role or put the hat on of a production scheduler, if you will, for a factory, we'll say. And so one of the things you get to do in that role is you dictate to the factory how much of the products to make. And sometimes it's also when each product is made. In this case, we'll talk about one planning interval there, or planning window. So it'll just be what we're making, we'll say, during that planning period. And so in this case, one of the things that we have the ability to control, if you think about it, is I have the ability to tell the factory how much of each type of product to produce. And so the products here are regular, deluxe, and holiday mix packages, if you will. A lot of stuff we're talking about is in terms of weights, in terms of how many pounds of each one of these products we're making. So that'll become our decision variables. And so I'll say something like, let's say X of R, X of D, and X of H. I'll say it's an element of the reals, be the quantity of regular, and this is in units of pounds, and this is to produced. Then similarly, we'll have X of D and X of H. This is the deluxe, I believe. Again, in pounds. And similarly with holiday. As well there. X of R, X of D, and X of H. Okay, so now we've described the decision variables, and these are in pounds, they're elements of the reals, which is kind of nice here. We're talking about nut type products, so that's relatively close to a real number there at this point. And so now that we've described the decision variables, now we need to move on to constraints and the objective function. Well, in this case, at the very bottom of the Jupyter Notebook there, you can see we're maximizing profit. So we could say we want to maximize some profit value here. And we're talking about the total profit contribution that's generated. And so we do have to be careful in this problem a little bit. There is kind of one gotcha that I can think of. So one of the things we might read is this statement here that tells us the profit contributions per pound of the deluxe, regular, and holiday mix. So that's nice. But then it also makes the statement of these contributions do not consider cost of nuts. Okay. Well, the problem also gives us up here the total cost of a shipment and the shipment amount here. So we could definitely calculate the cost per unit pound of nut based off of the shipment. So one might think that, okay, I need to calculate that cost and I'll subtract it from each one of these profit values to get kind of a net profit value. And then I'll put those as the coefficients in my objective function. I totally understand that logic. But one of the things we have to be careful with is this statement also up here, that the company is contractually obligated to accept the shipments regardless of any product production. So the reason you have to be careful with that is because in this problem, we would consider that something called a sunk cost. By a sunk cost, what I mean is it should not appear in the model because it is going to happen regardless of any action we take. No matter what the value of these decision variables we take at the optimal solution, well, we're still going to have to pay out for these shipments that we receive that are contractually obligated. So with that being in mind, that allows us to use only these profit contribution values, knowing that the cost of the nuts is happening no matter what we do. So hopefully that makes sense. And just to take away that when you write these LP models out, any sunk cost, costs that don't really have a effect on the model itself that are happening regardless of any decisions that you're making should be kept outside of the LP model. So with that being said, let's go ahead and write a objective function to characterize the total profit. And so I'm seeing here $1.65 profit contribution for every pound of regular. So it'd be at 1.65 X of R plus 2 X of D plus 2.25 X of H. So again, this basically gives me total profit. So that is a good objective function. Now we write ST as in subject to and subject to the constraints. All right, so the constraints, The immediate one that jumps out to me is the fact that we're making something, in this case, these product mixes, and we look at the raw materials and we only have a certain amount that's going to be available. We'll say it's an inventory, so to speak. And that's shown right over here. We have a certain amount that I can draw from, and then that's the right-hand sides. Now the left-hand sides will come from the bill of materials section, if you will, which is this table here. So we're going to have to write a constraint to make sure that we do not run out of almond, Brazil, filbert, pecan, and walnut. And I should be, I guess, clarifying when I say do not run out. I do not try to pull a negative inventory value there, because conceivably I could use up all the inventory and it becomes a binding constraint. All right, so let's go ahead and write one for the almonds. Well, we know the right-hand side is going to be 6,000. And then the left-hand side, well, we're going to have to use this column here. This is the percentage of almonds in a regular pound, the percentage of almond in a deluxe pound, and the percentage of almond in a holiday pound. And so since it's a percentage of, I can multiply each one of those percentages times the total amount of the regular, deluxe, and holiday and end up with an appropriate unit of pounds that is being consumed of, in this case, almonds. So I'll write that as 0.15 exabar plus 0.20 x of d plus 0.25 x of h is going to be less than or equal to 6,000 from here. Again, making sure my units all play out. That's all in pounds, so that's good. And then we would do the same thing for the remaining one. So I'll just quickly do that. I got 0.25 x of r, 0.20 x of d, 0.15 x of h, less than or equal to how much Brazil do we have? It appears to be 7,500. And then 0.25 x of r again, 0.20 x of d, and 0.15 x of h. This is for the filbert, so 7,500 again. 0.10 x of r, 0.20 x of d, 0.25 x of h, less than or equal to 6,000. 0.25 x of r for the walnut is now what we're on. 0.20 for the deluxe, and 0.20 for the holiday. And that's 7,500. Make a few notes here just for those that are going to look at this later. This was almond, Brazil, filbert, pecan, and walnut. I'll say all these are inventory constraints, essentially. Okay. So hopefully that's making sense, and we've seen very similar things before. And then the last set of constraints, I'm kind of looking at the very bottom table of that problem statement, and it's dictating lower bounds associated with our decision variables. These are minimum order quantities, assuming that we want to essentially keep those customers happy since we've already accepted their orders potentially. So we would want to force the decision variables to be at least those values. So X of R would say must be greater than or equal to 10,000 pounds. X of D is greater than or equal to 3,000 pounds. And X of H is greater than or equal to 5,000 pounds. In this case, I look at it and I say, okay, write non-negativity constraints. Well, I've kind of already done that, if you will, seeing as each one of these variables is capped at a lower bound of 10, 3, and 5,000 there. Other thing, just kind of stylistically, the way I've written this, you'll see this if you go look around at other textbooks as well. A lot of times they'll try to keep decision variables, especially with problems this size that aren't terribly large, where the like all the columns here line up. So x sub r, x sub d is falling in that line, x sub h is falling in that line there. That's kind of why I wrote those bottom ones staggered the way they are. Okay, so that is an acceptable LP model. I think if I look at the notes down here, I think I probably have also written the non-negativity ones probably. I slide down here just to make sure we're on the right track. Yep, that looks about the same. And then I've just also reinforced that non-negativity bit there. Since we're going to be talking about multiple things, let's go ahead and use Excel to actually solve the model here. So I'll just use this as a guide here. So given the time, let's go ahead and use this to just kind of show how this needs to be set up from more of a data side of things. So I can just say data here. Let's look at the product and orders pounds. We'll start with that one. There's kind of our first table. Then we'll get this table here as well. Just again, I've kind of reiterated this multiple times, but like this idea of typing into a workbook, most likely you would not be doing that if it's a real problem. You typically want to, especially if you're outside of the kind of initial prototyping stage, is to get it to where this is getting pulled from a database or maybe a flat file that you're getting from a SQL export, something along those lines. Just that this can be very tedious and also error prone as you're having to type through all of this data. All right, so there's that. And I think I'm going to go ahead and invert this table or transpose it, if you will, just so I can take advantage of consistent orientations. So like here, I'm going to say type of nut, and we'd have shipment amount, shipment cost. Think about like that. All right. So there's the data part for it. Almost. I'm going to go ahead and add to this table the profit contribution, and this is per pound. Just need to be clear on that. So we could have something about like this. All right, so if I can slide this over a little bit, be able to show our model as well. Go. So model, we'd have decision variables. And again, I try to keep as much of this formatting as the same. So I have something about like this. These are my decision variables. I'll have an objective function where I want to maximize some unit profit contributions. So in this case, I'm going to use sum product. I think I introduced that last week. So I can take this and this, and it'll take the sum and the product of each one. So again, that's this cell times this cell plus this cell times this cell plus this cell times that cell there. So that should be a good thing for us. And notice the orientation is the same, and also the ordering has to be the same there. So make sure to watch that. Constraints here, left-hand side, right-hand side. Looks like I end up with what? 5 and 3, 8 constraints. Think about like that. The first ones are all going to be inventory. So there's 5 here. And really, I would suggest a better comments than this, but I'll just do something like this for now. But it'd be nice to say like almond inventory, Brazil inventory, filbert inventory, so on and so forth. We need the inventory amounts. That's this value. I'll transpose those. And then the left-hand side needs to be what? This, which is the percentages of almond based off of how much of the products we make. And we'll do a sum product between that and this. And so we'll have a few different sum products here. This one for the almonds. That one for the Brazil. This one's for the filbert. The pecans. And the walnut. All right. And then we move on to the minimum orders, which is fairly straightforward here. I'll just copy again these, but you may want to say something here. I guess I can group some cells if I wanted to say inventory. So to quickly and easily state here, minimum orders. And we would get these from here. This is the minimum order column that we just put in place. And these would just be the values of our decision variables on the left-hand side. All right. There we have it. And so we've got the data representation over here, the model here, and now we just go to the solver. So I'll go to data solver. I'll set up my objective as we usually do. We want to maximize, that's great. I want to change those cells for decision variables. And we'll need at least 2 families of constraints in here. One family for all the less than or equal to, right there. I'll hit add, and then one for the greater than or equal to associated with the minimum orders. And I'll hit OK at that point. All right, so that all looks good. We do want to make unconditional variables non-negative, and we'll say simplex LP solver. So at this point, we're all good to go. So we'll solve the model. And we end up at a result. So that's all looking good. Just given the nature of the lecture tonight, I'll go ahead and show the reports. So I can do some formatting. Say, okay, that's actually interpreted as dollar amounts. They put a comma in here. The maximum profit contribution looks to be about $61,375. Here is the distribution of the regular, deluxe, and holiday production load, so to speak. We're going to make 17,500 pounds of regular, 10,625 for the deluxe, and 5,000 for the holiday. This was last week. This is where we'd stop and say, hey, we did a good job. But this week, there's a set of questions that come with this case problem. And so we need to try to answer those. And so I'm looking down at the book. Now, I look at question 1. They talk about a managerial report you're going to be writing. The first thing they talk about is the cost per pound of the nuts included in the different mixes. This is kind of a weird question to ask just because of the way this problem falls out. Because the cost per pound would basically be, where are we at here? Here we go. Here, where I could say something like shipment amount, I'll say unit cost is this number divided by this number, because this is dollars per pound essentially. There. And so it's asking us to compute those values. The reason I find this a little bit weird for this problem is because those values, those coefficients don't show up in the LP model. But again, if somebody was asking, they could say, okay, yeah, that would be the cost per pound. That's reasonable. The question 2 is the optimal production mix and the total profit contribution. Well, that's basically the data right there that we just solved. So we've got that. Number 3. Recommendations regarding how the total profit contribution can be increased if additional quantities of nuts can be purchased. Okay. So they're basically saying, okay, what if I could get additional quantities of nuts? Basically increase my available inventory. How would I choose to increase it? Like, which nut do I try to pursue more? Do I try to pursue more of almonds? Do I try to pursue more of Brazil nuts, filbert, pecan, walnuts? Which one do I pursue? Which one would be of best value to pursue? And so hopefully, given a nice lecture, you're basically saying, okay, we're talking about the constraint section. We're talking about right-hand sides of constraints. Hopefully you narrow in very quickly that we're talking about dual values or shadow prices. And so if you remember, those are down in the sensitivity report. And so I start looking around, and one of the things that catches my eye is this guy right here. This is a constraint. It's in J18. Row 18 appears to be the almonds. And notice it has the highest value for the shadow price. For every 1 more pound of almond that I'm able to acquire, my objective function value is going to increase by $8.5. And that's a good thing. So I'd be definitely pursuing some almond nuts. The other one that also is showing a non-zero shadow price or dual value is the one represented by row 22. And if I go to row 22, walnuts, they have a dual value of 1.5. Not near as good as almonds, but still beneficial all the same. All right. All right, that allows us to answer number 3 as far as tells us what type of almonds we'd want to secure. Number 4 basically says a recommendation as to whether the company should purchase an additional 1,000 pounds of almonds for $1,000 from a supplier who overbought. Okay, so now we were presented with the opportunity to buy some almonds. So we can buy some almonds here. We can get 1,000 pounds for $1,000. Basically buy them at $1 per pound, which is noticed less than the value that we just paid for them, $1.25. So if I look at this, hey, that's great because remember this cell or this row here in the constraints table with respect to almonds. Put this out here. This is almond inventory. And they're saying, okay, I can get 1,000 for 1,000 pounds for $1,000. Okay, that's great. It definitely has a positive value for the dual value. But notice that increase of 1,000 exceeds the range of feasibility, right? Because I can only increase by 583.3 and have it be increasing the objective function at a rate of 8.5. So what I would suggest doing at this point is taking that 8.5 and multiplying it out by the allowable increase. This basically is the largest amount that I can extrapolate. And I look at that and I say, well, that says $4,958. So what does that mean? Okay, if I could get 583 pounds of almonds, I would expect the objective function to increase, getting close to $5,000. Seeing as that $5,000 is much greater than the $1,000 price that I would be buying for the almonds, that would definitely give me the confidence to go ahead and make that suggestion to management, whoever has to give them the authority to execute that deal, is to go ahead and buy the 1,000 pounds of almonds for $1,000, given the fact that I know that if I just had 583 pounds of almonds, it would increase the profit by 4,958. So that's how I could reason out from the sensitivity analysis. If I wanted to, given the sake of this model and how quickly it is to solve, I could go ahead and put in the 7,000 pounds for the constraint and just confirm, okay, what would my profit be for that? And then I may have to have the discussion, okay, this is the profit not considering the $1,000 extra that I'm now paying for that new shipment, if you will, of almonds. The last question, question 5, recommendation on how profit contribution could be increased if TJ Inc. does not satisfy all existing orders. So since it's talking about not satisfying all existing orders, we're talking about these guys down here. We've got these last 3 constraints that had to do with the orders themselves. If we're not satisfying all the orders, we may be falling short on some of these minimum values that we've had. So now we're talking about the right-hand sides of constraints. So your mind should be going to dual values. 23, 24, and 25 are here. So this is regular product, deluxe product, and the holiday product here. Well, if I look at them shadow price wise, those two are 0. So manipulating the right-hand side of those doesn't really change the value of the objective function. But notice this one here is at negative 17.5 cents, essentially, since we're talking about a objective function in dollars. Well, that's basically saying if I was to increase the right-hand side constraint from 5,000 to 5,001, I would see a decrease in the overall profit. Well, conversely, if I decrease the value that I'm going to produce, so instead of making 5,000, I make it 4,999, one less, I would see the profit go up by this value, a negative of the dual value, so up by 7.55 cents. So this would be one area that if I felt that I could not fulfill the existing product orders, that I may want to do that because this holiday mix is taking away some of the other nut material away from other products that it could yield a more higher profit overall. And notice if I look at the range of feasibility, this can be extrapolated all the way down to 0, right? I go from constraint right-hand side of 5,000 and my decrease allowable is also 5,000 there. And so that would be my suggestion to the management. Okay, if you really want to, I mean, this other also involves implications for how the customers are going to react to this. But conceivably, I could extrapolate that down and say, okay, the profit could increase $875 by just not fulfilling any of the holiday orders. Again, that could potentially be short-sighted because now you're going to potentially decline a bunch of orders that you've already committed to, and there's also implications with that as well. But that's definitely outside of the scope of this mathematical model that we're trying to work around. All right, so with that being said, I'm looking at the textbook down on the floor. That completes the model and case problem that we are talking about this evening. So at this point in the lecture, I've covered everything for the evening. It's a little bit shorter lecture for tonight, and so we'll get out a few minutes early. But I'll kind of turn it over to you guys as a whole for the classes, see if there's any questions you guys have for what I've covered this evening. I'm not really hearing any questions there, so I'll go ahead and turn back over to Chrome browser here. Okay, put on the comments. And so I guess at this point in the semester where I typically turn it over to the homework sets. And as you can see, it looks like I have a little bit of homework from grading for the chapter 2 homework. And then also, for the usual, you've got chapter 3 homework set here. It should be open in Canvas. 2 attempts. Open now, just a little bit ago, and then due in a week. So that's the task for the week. Next week, most likely, I should be back on campus to talk about chapter 4. But I'll definitely firm that up in the weekly email announcements that I put in the beginning of the week. The other thing to do, I think, is I've had a request to kind of page through the homework set. So I'll just go ahead and do that now in case anybody needs to look at it that way. Looks like there is a graphical solution there, so that'll be doing similar stuff to what I was showing earlier in the lecture. And that is about it. All right. So again, thanks for joining me live for the lecture this evening, even though it was remote. Hopefully you guys have been able to still get some quality information out of the meeting itself. If you have any questions, I'll keep the meeting open for a few more minutes, but if I don't hear anything for several minutes, then I will go ahead and shut down the meeting. So with that being said, if you don't have any questions, good night, have a good week, and I will talk to you in a week. Okay, no, I'm not really hearing any questions at all, so I'll go ahead and shut down the meeting at this time.